So PCO2 derived indices, and I have no conflict of interest to disclose for this presentation. What's the basic problem? We all know that circulatory failure may result from either a decrease in cardiac output and or a decrease in the perfusion pressure of the organs that may lead to tissue hypoxia. And it is not possible to take care of patients with circulatory failure without detecting tissue hypoxia and without evaluating the degree of tissue hypoxia to adapt the dose of our treatments. So, which markers, reliable, precise markers of tissue hypoxia may we use? We have three main biological markers. SpO2, very interesting, but we know that it might be unhelpful in the large majority of septic shock patients because of oxygen extraction impairment. We have lactate, very sensitive, but many false negatives, and it reacts with delay to oxygen consumption changes. And so are the PCO2 derived indices able to solve the limitations of the two other ones? And more precisely, what's the basic physiology of this PCO2 gap, the well-known PCO2 gap? Can we use it as a marker of tissue hypoxia, and how to overcome the limitations of it for detecting tissue hypoxia? Let's start with a very basic physiology of CO2 transportation. CO2 is produced in the mitochondria, which diffuses toward the cell, toward the red blood cell, where it reacts with water. And this leads to the production of bicarbonates and an H+ ion. Bicarbonate diffuses out of the cell, and the major part of CO2 in blood is under the form of bicarbonates. There is also a solved CO2, a dissolved CO2, and a small part is linked to the NH3 extremities of proteins, including the globin of hemoglobin. But the main form is under bicarbonates. By the way, the H+ ion reacts with oxygenated hemoglobin, and the free oxygen then diffuses toward the mitochondria. On the lung side, it's the opposite. Because of the high concentration of oxygen in the alveoli, oxygen diffuses through the red blood cell. A reduced hemoglobin is oxygenated, and we have the opposite reaction where bicarbonate and an H+ ion form CO2. CO2 is also dissociated from the NH3 extremities of globin, and CO2 eventually diffuses toward the alveoli and is eliminated. In other words, CO2 is produced by the cell metabolism. It is transported toward the lungs through cardiac output, and eventually it's eliminated through the lungs. In other words, there is a gradient between a high PCO2 gradient or partial pressure at the venous side and a lower PaCO2 or CO2 arterial content. And the PCO2 gradient or the PCO2 gap or the delta PCO2 is the difference between the venous and the arterial PCO2. What are the determinants of this PCO2 gradient, and how may it help us assess tissue hypoxia? In fact, it's very important to bear in mind there are two main determinants of the PCO2 gap, cardiac output and cell metabolism. Cardiac output, because it's easy to understand that if cardiac output is high, more CO2 is transported toward the lungs, and more CO2 is finally eliminated, and the PCO2 gradient is reduced. In other words, one can express that with the Fick equation, VCO2 equals cardiac output times the difference in CO2 content between veins and arteries. It's quite difficult to estimate the CO2 content at the bedside, but we can measure the CO2 pressure. And there is a relationship between the CO2 content and the CO2 pressure. Interestingly, in the range of normal PCO2 values, you see that the relationship is almost linear. Of course, CO2 content does not exactly equal CO2 pressure, there is a multiplicating factor, but we can say that VCO2 equals cardiac output times a multiplicating factor, the key factor, multiplied by the PCO2 gradient. This is expressed by this relationship between the PCO2 gap, y-axis, and cardiac output, x-axis. And you see that the higher cardiac output, the units are not the right ones, the higher the cardiac output, the lower the PCO2 gap, and you see this exponential relationship. The second determinant is cell metabolism. And here one must consider two different conditions. Under normoxic conditions, CO2 is produced by the oxidative metabolism. The more oxygen is consumed, the more CO2 is produced. And this is tightly linked, mathematically linked, if I may say, through the respiratory gradient. So the main determinant of the CO2 production, the only determinant of the CO2 production, is the oxygen consumption under normoxic condition. Under hypoxic conditions, of course, there is no more oxidative production of CO2. But CO2 is produced in excess because of acids buffering. I mean that because there is no more oxygen, no more mitochondrial respiration, the respiration of the mitochondrion is interrupted. Pyruvate accumulates, lactic acid accumulates, but it's immediately buffered by bicarbonates, which produces CO2. And also the hydrolysis of ATP also produces H+ ions that are buffered by bicarbonates, which again produces CO2. An aerobic metabolism produces CO2 by buffering of the produced acids, and this may increase the PCO2 gap. Then it's okay. Let's use this PCO2 gap as a way to detect tissue hypoxia and to quantify tissue hypoxia. Is it actually possible? Could we do so? Can we use the PCO2 gap as a marker of tissue hypoxia? And that's the point of this presentation. The answer is no. The PCO2 gap is not a straightforward indicator, marker of tissue hypoxia and anaerobic metabolism. The most obvious reason is this one. Yes, CO2 is produced because of acids buffering, as we've seen, but also, as there is no more oxygen consumption under hypoxic conditions, less O2 is consumed, which means that less CO2 is produced, and you see that both mechanisms tend to oppose each other. Also, even if CO2 would be produced in excess, it is easily removed by cardiac output, provided that cardiac output is not too low. By the way, it's exactly what expressed on the relationship we have seen. You see, it's only for very low values of cardiac output, and I'm sorry, again, there is a mistake in the scale of the x-axis. Only for very low cardiac output values, the PCO2 gap eventually increases. And also, the key factor we have seen before is increased, especially because of acidosis, which tells us that, and it's a point, the PCO2 gap is not a straightforward marker of tissue hypoxia, but it expresses the ability of cardiac output to remove CO2 toward the lungs. It's basically a marker of the level of cardiac output, shown by many studies, but for instance, in this septic shock patient study by Bakker and Jean-Louis Vincent years ago, you see that the PCO2 was normal in a large proportion of patients. And interestingly, the patients with normal PCO2 gap values were the patients with the highest values of cardiac output. Cardiac output was easily able to remove CO2 from the venous blood. So it means that let's use it as an indicator of the level of cardiac output. If PCO2 gap is high, it means that it's a it might be a good option to increase cardiac output, and we may follow the treatments aiming at increasing cardiac output with the PCO2 gap. But basically, there is a limitation for considering the PCO2 gap as a marker of tissue hypoxia. A good way to overcome it is to consider that basically you agree that what you want to detect is the production of CO2 due to acids buffering. In such a case, it means that the production of CO2 exceeds the oxygen consumption. On the opposite, the fact that VCO2 decreases because of the VO2 decrease expresses that in such a case VCO2 equals VO2. So let's calculate the VCO2 over VO2 ratio. It's increased in case of mainly of acids buffering and as a main mechanism in case of tissue hypoxia. This is in fact the respiratory quotient. How to estimate the respiratory quotient at the bedside? We do not have indirect calorimetry, but we know that the PCO2 gradient is linearly linked with the CO2 content difference. So if we develop the Fick formula, if we eliminate cardiac output from both sides, if we estimate that the CO2 content difference can be estimated by the PCO2 difference, we come to this ratio, delta PCO2 over the delta content in oxygen, which might be a marker of anaerobic metabolism. The first study to show that it's actually linked to lactate was this one by the team of Armand de Saple and Jean-Louis Deboul years ago. It detected the low values of cardiac output. In this study by Mesquida and Artigas, they showed that patients with a large clearance of lactate had the lowest values of this ratio, delta PCO2 over the delta oxygen content. The advantage of a lactate might be that it reacts very rapidly. And in this study, we showed that we wanted to know which variables indicate that oxygen consumption improves with fluid administration, as VO2 was unable to detect it because it was normal in the septic patients. Lactate decreased, but it took time. We measured it 6 hours later. Why? The delta PCO2 over delta O2 content ratio decreased immediately. To finish, there are some limitations. First, estimating the delta PCO2 through the delta CO2 content is reasonable, but not in some cases. This is a study where you see the hind limb of dogs were made ischemic, okay, or oxygen was reduced. In any way, there was hypoxia, and you see that for the highest levels of hypoxia, on the bottom side, the difference in CO2 content decreased, while the delta PCO2 increased, falsely increased, if I may say. And it's likely because there was acidosis, large acidosis, explaining that CO2 was moved away from hemoglobin and that it was eventually, it increased the PCO2 gap, but not the CO2 content. Be careful in case of high lactate values, of low pH, I'm sorry. Also, it's only one study, but they showed here that the precision of the ratio is not that very good. You see, the delta PCO2 over the delta oxygen content ratio was not very precise. The smallest change that could be detected was a 38% change. We need some more studies, and for sure it is less validated than lactate and SVO2, but at least it might be interesting for solving the limitations of SVO2 and of lactate. If SVO2 is low, we know we should increase oxygen delivery in patients with shock. If it's high, we don't know. It might be tissue oxygen impairment, oxygen extraction impairment. Let's consider lactate, but there might be some false positives, and here is the place for this ratio, delta PCO2 over delta oxygen content. If it's high, it suggests we should increase oxygen delivery, hemoglobin, PaO2, fluid to increase preload, and inotrope to increase contractility. Thank you very much for your attention.